All right. Let's keep moving. In the break, Ozai pointed out that this quantity here is used quite a bit in Kepler kind of situations, right? Huh?
Yes, to describe planetary motion.
To describe planetary motion. So they actually don't use this law here, but they use this one too, and they look at the velocity of the planet,
Yeah.
right? And then they relate the angular momentum. It is one of those that area law,
Yeah.
right? The equal area law, huh? The Perkewet in Dutch. Huh?
And then what was the thing that doesn't work for rigid bodies and does work for planets?
So I believe they can do this in Kepler laws because because the moment of inertia is mr squared. And if for example you have a cylinder with mass, then the moment of inertia becomes 1/2 mr squared, I believe.
Yeah.
So you get constants wrong and things.
Yeah.
Like that.
Okay.
So they can do this because the body that they're considering all the mass at the circumference
At the rim of
of the rim of the object.
Yeah. So we'll have a situation like that too here. So we'll find that all our masses are distributed like that, huh?
But not in rigid bodies. We don't.
No, but I
model it
mean
as
in
rigid
ALM,
bodies,
the
yeah.
ALM,
Yeah,
simple
yeah.
ALM thing. You can consider that you have multiple. I guess you could have the other one too, huh? But anyway, implicit in the assumption of using Macaulay duration is the idea that you just have this one, bond, huh? So we can do both, I guess, huh? Depending on the financial situation. Okay, so let's keep moving. Something new over there. Where did that come from? So this is the same slide, except here I just drew it out, okay, what everything is that I tried to do in a little squiggle over there. So you can see that here is our principal, huh? This is the interest, and this here is our risk aversion factor. So I just put this mass right here, okay? So this is the risk aversion factor that belongs to this movement here. I'm going to keep this Q0 constant, okay? This distance here. So you're not putting any more money, you're not taking any money out. Huh? You're not repaying your loan, and you're not borrowing more. Then this will be the amount of interest. This will be the price. Huh? So this is the risk adjustment factor for this. Huh? And this is the way we can look at the interest rate. So I just used the regular right-hand rule, kind of, it's coming out of the board like that. Huh? You can also think of it as this area. I like that. This is the typical engineering way. And similarly, you will see that the value, the price of the bond is also sticking out in this way, right? So you could write this Q0 and then the cross product, I guess, with the P1 will give me this as a vector, huh? And now I look at these as a vector. So you see that, well, and then this thing has you can just see this as a rotating body. The rotation is a little funny here. The rotation is more a line, it's not going in a circle, but that needn't bother you, all right? So the bob is over here, you'll still have this. If you divide it, it's still the angular velocity. So don't get confused that it's not going in a circle, all right? So it's just going along this line. We're keeping this constant. This is sometimes called a holonomic constraint, okay? So this thing is going on a submanifold, and you can see it goes at constant speed. So if it does, then this momentum will be conserved. And if you get normal interest gets paid all the time, what does that mean? The price doesn't change. As soon as the interest starts going up or down, the value of the bond will change. That's precisely what you want, okay? So you will have an equation that says the value change, right? Yes. can't write beyond a certain point here. So the value change is equal to the money duration times the change in interest rate, right? So this is just, what is this thing? What's the derivative of the angular momentum? What's this, huh? What's the time derivative of the angular velocity? Angular acceleration, right? Huh? Do they have a symbol for that? Alpha? Yeah. Now this is just Fz times A, but then the torque, huh? A. I see. So this is an extremely important figure for the banks, okay? Because they want to look at changes in their net worth. And that's why they look at this. And of course, their net worth, what does it consist of? Well, the value of all these assets they have in there. And if this is the value of the asset, they want to see how that is changing. Right? So our regular old Fs times A gives us here an extremely important piece of the mechanism, okay? All right, let's. Well, it is already full screen, except if you have it on draw, somehow it doesn't decide. This is not easy to learn, this thing. Huh? You have to develop a relationship. Okay. Okay, having said that, we can now do our usual bond graph stuff and everything, and we can keep track of value changes in our capital accounts or our loan accounts or everything, just using bond graphs, right? Because we just have an I element, we have a C element, we have a Lagrangian that tells us what these elements are doing, and we can keep moving. Okay, so first for a couple of definitions, the value or the price is just now the marginal utility change over a change in the interest rate. Huh? Okay, that's always the price of everything, right? The change in utility per change in the stuff you're getting, and that's now an interest rate. It's not the amount of interest income. Okay, that's the angular momentum. And that's just the price of this bond, the value of this loan, okay? Then you can look like the convenience, and it's sort of a torque, right? It's like the spring force, the spring torque, really. So if you have one of these spring systems, you have these springs, these little coily things, right, rather than a linear spring. And the moment of inertia, which is the duration, you just get by two derivatives. So you got everything right here. And your total utility is now going to depend on your interest rate and how much interest you have. Remember, Q0 is a constant, right, here. So if we reduce the problem in 2 dimensions to one in 1 dimension, it's just about the interest rate and the risk associated with getting it or not getting your interest, okay? And we can track the change in the price of the bond and with the interest rate. So the higher the interest is, the less this stuff is, you want to borrow money, right? Huh? And the supplier is exactly the other way around. Huh? The higher the interest, is like nice and valuable to you. Huh? And you can now look at the convenience too. There's a sort of a torque acting on it, So it's saying, like, if you have accumulated a lot of interest, you're a little bit less interested in getting it. Okay? And there you are. So here, all these variables find their home, right? So with the I element, that's the duration. So this gives you the duration. Yeah? and it holds the value of the asset or the liability. And if you apply a change in value, then you will see that it will change the interest that it will be willing to pay for the asset, okay, or liability. All right. And the C element works similarly. So what's important here, if you're making bond graphs of financial systems, you can just switch to this rotational analog, and you can just use bond graphs like that. So don't get stuck on the idea that they're all only for commodities, okay? And then you can do your regular kind of stuff, you know. I made some remarks here. Once you have this setup, suppose your utility only depends on the interest alone, you know. You don't care how much you've received of it yet, you know. That's very typical, you know. Most banks are like that, you know. But most demanders of a product are like that. If you look at a partial equilibrium and you've already eaten in your life 1,000 apples, what does it say about what you're going to eat now? You know, nothing much. You know, you could have a lot in storage, but a lot of people don't have nothing in storage. So you just let your utility depend only on what you're getting in. Then you get this, you can prove something that's called the law of conservation of angular momentum, which translates just in price stability, okay? So that means that the price of a bond will not change, you know, stay constant in an environment where there are no torques, okay? I just have this as an interesting note that all these ideas of these various laws translates to something that is quite compelling in finance, okay? This idea of price stability, which is the market in equilibrium. So the prices of all the securities stay the same, all right? And in this case, we'll say, well, they will say the returns are the same, or in this case, the interests are the same because these are interest-bearing things. We're talking about bank. We'll just say everybody is in equilibrium. But what it really means is we're all in rest, you know? So this thing is just going at a constant speed, you know, it's maintaining its, you know. Oh, and here for superfluously, I just wrote down that is the law of demand, but now for money, okay? So there's a law of demand for money, and it relates, you know, money to its price, the risk that you're bearing on the money, you know, through this type of law, okay? And it's just the Euler-Lagrange equation that comes out of our Lagrangian system. So here we are, we have a nice Lagrangian system. We can translate it into this bond graph, and we have all kinds of standard stuff that we all know kind of falls out of it. It all works, okay? So we've gone from something very complicated, Q0, Q1, we took, for a second, we took the assumption that the amount of funds was a constant, and then we find a very simple kind of system, okay? That we're very comfortable. But that doesn't mean that in practice it's so simple. And in practice, the bank has at least two masses, okay? So here's what they do. They have assets and liabilities. What are the assets? Suppose you're a bank and you loan some money to some business, a startup or whatever. They got to pay you money. They got to pay you interest. That's an asset because you have a claim on those people. They got to pay that money back. So that's an asset to you. All right? The other way you know it's an asset is because by holding that contract with that business, you have a right to all the benefits that ensue from it. That's normally the definition of an asset. And what are those benefits? Those benefits are exactly the interest payments that are due on it, okay? So an asset is something that confers benefits in the future. So the loan you extend to somebody is an asset because it confers benefits to somebody, to you. You get the benefits, okay? The other part of a definition of an asset is that you would bear the risk with it. So you don't get these benefits for nothing. So an asset is defined as something for you have the right to the benefits, but you have the obligation of bearing the risk. So if this guy doesn't pay, it's on your account. You can't go cry to somebody. Of course, banks do when they go to the government, but this is not really the idea, right? Huh? They should be independent. Huh? Okay? Now, the other side of this balance sheet, you have something called a liability. So suppose you're a bank and somebody like you deposits money in the bank. Then what is happening here? You don't have an asset, you know. You have a liability because you have to pay that money back to that person. So you're liable for the total amount of Q0 that you put in there, if I'd say it this way. Huh? Okay. And that liability, it confers on you the duty to pay interest. Okay? So the asset, you receive the benefits, and for a liability, you have to give the party the benefits. So you borrowed money. If you borrow a car or you loan a car, you got to pay the rent, and if you're and it's the same with money. Okay. So there are two sides of this. On the asset side, where you have some kind of security, maybe it's not a security, it's just a loan, and that I plotted here on the right side. Okay. Normally, an accountant will put the assets on the left, but that would mess it up because I like to think of it as a positive number. Okay. And then the interest income I just called now V sub A. So I dispense with this 1, right? I'm just assuming that you can see that this is interest income. Okay? And this is the risk aversion characteristic for me of loaning to that guy. Okay? Huh? My customer. Here it's the other way around. I borrowed money from somebody. Okay? So I got to pay interest. That's my liability. So this is an L. All right? And how much did I borrow? This much. And how much did I loan out? This much. Okay? So if you look at a balance sheet of the bank.
So are these values of the banks by the bank or by the person that they're lending money to?
Yeah, usually it's the bank itself that does this if you're the bank. Now, what the contract will stipulate, I don't know yet. But what the question here is, me internally, what am I willing to do, right?
So but does it depend, for example, say you and I both go to a bank,
Yeah.
they would use this model to,
Yeah.
so would they have the same mass for you and mass MA for you and me, or would they be different?
No, they will be different, right? They would think you are more risk, or that, they'll definitely be different. This is just you. And it'll be me, or you throw them in one class. In principle, it's all different. In practice, a lot of it is the same. Okay? In principle, everything is different. But I think in practice, you just say, these type of guys will do this. Huh? I mean, look, the real answer is it's up to you to decide when you make your model. I mean, if you have a rigid body, every point is really, it's not really rigid. At what point do you say this is the same and it's different? Huh? It's just up to you as an engineer to make the decision. Huh? I mean, Newton said that every point particle is different, right? Huh? And then with a rigid body, you say, oh no, I can view them all together or something, Huh? So I would take a more practical approach to the answer of this question. You see what I'm saying? I mean, in principle, everything is different, but it's precisely the choice you have to make, okay? But what this figure wants to say is there's a difference between assets that I drew on the positive side and liabilities that are on the negative side, right? Now, banks will call this also a positive number, so then this thing gets flipped if this is negative, you see? But you know, and then you can see the balance of these things a little bit better, but that's just not how we do it, okay? Huh? We have this as the arm and then, huh? Okay? So this is our picture of what happens in the bank, okay? And how, so this is sometimes called a two-body problem. So you have two bodies and they're connected through some central force, right? And here it's a trivial two-body problem. I'll move to the non-trivial one because I just bolted them together, okay? And I constrained them. All right? So for us, this is nothing super exciting. So you can easily see this thing is going like that. So when it's going, you know, the angular velocity is this vector here. You can look at the total angle that this thing is made and whatever, right? And you can also see that this thing is longer than that. And maybe this mass I drew a little bit bigger than that. It's hard to see, but if you looked at my TIC Z code, you would know the difference, right? So you would see pretty quickly that the center of mass, I probably drew it, it should be around here, but whatever. It should be a bit to the left. And you know now, you don't need much of an engineering mind in order to sort out how this thing is moving. But now let's look at it from a banker's perspective, what they do, okay? And that's what this is about, and I wanted to go through that, okay? And then we can, so they do something that they call gap analysis. So this is points to the problem that I already said. Like if you know that the change in value is related to the change in some interest rates, huh? You'll know that if one of these things is changed, something has got to change with this other thing. Right? And how much is that? You know, what are the forces acting on this thing and how is this thing going out of control? Because the total value of your company is the value of your asset minus the value of your liabilities. And if you subtract those, you get your net worth. Okay? So they're very worried about this situation. So let's look at how they attack it. They do two kind of things. They do what they call basic gap analysis and duration gap analysis or standard gap analysis. So let's first look at the basic gap analysis. So first they'll say, what is the gap? Income gap, they call it. And they'll say, well, they actually subtract the liabilities from the assets. Now I have a plus sign, but that's only because this thing is a negative number here. All right? But basically you're subtracting them. So what does that mean when you have a gap? That means you have more assets, more income earning assets than you have income losing liabilities, all right? And that they call the gap in their balance sheet, all right? So you can see here the gap is positive, right? So this gap also, you can see it as the dislocation of the center of mass from the regular center of geometrical center. Pardon?
Central of momentum?
Yeah, or just the geometrical center, right? So you have the distance in the center here, and then the gap. See, if this gap is 0, that means you're in the middle, right? So that's okay if assets are equal to liabilities. If they're not, you're going to have this gap. You know, so the displacement of the center of mass or the center of momentum, I think, is equivalent here.
Here it's equivalent.
Here it's equivalent, right? So this displacement is what they call the gap, right? So this is center of mass versus the center.
But isn't that under the assumption that the mass are equal?
This is just a definition. This is just what they call it.
If one of the mass is extremely large, then
No. That's this question of standard gap analysis. This is the simple thing. This is what they call basic. They don't go look at the masses, right? I see where you're going to. You're saying, look, if the masses are unequal, this doesn't tell you that much. But this is just a definition. It says what it says, you see? So your problem is okay, except that's not what the point of this thing is. That's just to make the definition of how the center of mass is displaced from the geometrical center. You see what I'm saying? It's just of interest to note that this is what they call the gap, right? Okay, huh? Because if that's the case, you see, then if this thing is going at, what they do is they keep the interest rate constant. This is a constant, right? Huh? They say, all right, the interest rate is say 5 or 8 or something, right? Huh? And then what you see is that if you subtract the flow of the asset minus the liabilities, then you'll have a difference. That difference is your income, your net income. Okay? Because that's the interest income you're receiving on your asset minus what's going out on your liabilities. All right? Huh? So you can then calculate that the rate of change of the bank income will then, be exactly this. Okay. I mean, nothing is happening. All right? All is happening here is we're taking some terms. So you go through a banking book, and they'll talk about their risks and ALM problems, asset liability management problems. They'll have these terms, and all I'm trying to do here is help you translate these terms to this basic setup. Huh? I mean, all I'm saying is if I'm moving the pivot point to the left here, this thing is going to go slower than that thing. And the difference of those two speeds, that is the net income of the bank. All right? Yes, because this is the interest coming in on the assets minus the interest going out on the liabilities. So this is not very exciting, huh? Or not very deep. What is of interest is to see that this picture that we drew, and we didn't even worry yet about the masses, already gives us some kinematics that does, the kinematic part already does you half of the job. All right? Huh? I guess that's my message. You guys are just too clever already. You're just wondering why I even bother. Huh? Right? Huh? What about those masses? And that's what they say. So if you read on, they say, well, but the problem of this is that you're not really interested in your change of income. That could be anything. But the bank is interested in whether it be solvent or not. What's the change in the net worth? Because the net worth goes negative, you're on the water and you go into bankruptcy. All right? So they want to not see just how you can be earn an enormous amount of money in your P&L, but if you're bankrupt, you're bankrupt. You got to run on the bank and you're gone. So they get nervous about not taking into account their solvency. All right? So they want to know what are these values doing of these assets. I don't care about the income, or they do, but huh? So you got to go, and this is the stuff they were not doing before the credit crisis very well. They would just say, hey, we're making a lot of income, let's pay everybody bonuses. All right? Oh, let's take more risk, right? Huh? Because they haven't modeled the risk, right? So they weren't taking care of prices. There's nowhere in this story are prices, right? That's why you don't see the masses. Huh? So you're just making all this income. It seems like banking is, it's free money. It's just free money, look. Well, it's free money if you didn't account for the risk, okay? Now what happens is, what you want to do is look at the net worth. So that's the value of your assets minus that of your liabilities. I only have these plus sign because angular momentum is a vectorial quantity. So it's kind of confusing, but I left it like this. All right. So this is just the net momentum, right? So the total of momentum. So here you see you can just add the momentum of these two guys. We all know that, right? This is the law of conservation of momentum. Then you can say the net rate of change. So I'll just look at the derivative of this thing. So I can define something like the net duration, which is the net moment of inertia of this whole two-body system, and you can just sum the moments of inertia, I guess, huh? Because of that, huh? Yes, you can. And you can just see how that is changing. And now the factor is this net duration that you have, okay? So that's the duration or the net moment of inertia that happens when assets and liabilities are interacting in this way, okay? And then you can see how your net assets are going to change. Your net worth is going to change, okay? This thing is called a couple, right? So there are two torques, but one acts this way, the other acts that way. So in ALM, what you do is you're looking at this, the torque of the couple. Huh? Isn't that interesting? Huh? And if you assume a rigid body, you can just add these, right? Huh? And that is the same assumption that these assets and liabilities do not change, right? So you're not prepaying or borrowing more. Then you have kind of a rigid body, right? And then you can just work with the same single moment of inertia. Of course, if you don't have a rigid body, the moment of inertia will change, right? So you know that governors and those things, they have these balls go out and then the moment of inertia changes, huh? So you can see in this very simple case where you're just balancing the interest that comes in, you can analyze this as a rigid body rotation of, and I just had two liabilities. You can have way more, of course, huh? And it's actually, you can calculate the reduced mass, you can do anything you like and figure out what's going on with their balance sheet. But now we're in business, right? Because now we can, there's no reason why it should be a rigid body, huh? We can just like pull a little spring here or whatever, huh? Make this a little, just extend this, like telescope it out, huh? You probably have to provide some force, now, that's okay, huh? So repaying or loaning more is probably going to cost you something, you have to pay more interest, so the thing will start speeding up, so you have these pictures. You always see them like this, where a guy here, huh? He's pulling at a rope and he pulls it in, right? Huh? This thing is bopping, huh? And then he tries to pull it in, and then it's not, you got to put energy in that thing, huh? So you can extend these arms or contract them. And what you do in this rigid body stuff is you get rid of, you have all these Q assets and the Q0 of the liabilities. But what you do is you just look at the sum of the two, right? And you call that the length of this arm. And you can change that too. And this has a name. This is called the size of the balance sheet. So you add the assets and the liabilities, and then they balance. If you sum them up vectorially, right, huh? Then it's zero. But if you just sum them up, the absolute values, what I'm doing here, right, huh? Then it's not going to be zero. And the number you get is the size, usually the divide by 2, right? That's okay. Huh? That's just either the assets or the liabilities, either the positive number. And so this is that, and that's what we do too. We usually look at this distance, and then we divide it by 2 for the effective radius, okay? Huh? But either way, whether you divide by 2 or you don't divide by 2, this is known as the size of the balance sheet. And changing that is known as expanding the balance sheet or shrinking the balance sheet. So what the ECB has done and the Federal Reserve with the credit crisis was what they do is they provide liquidity in the system. So their liabilities, they consist out of money and circulation and those things, right? Huh? And their assets consist of all these government securities that they buy. So what they do is they provide liquidity. They buy bonds or other stuff, and they buy it with money they print and put in circulation. They don't really print it. They put it in bank accounts, okay? So they swap long duration assets for short duration assets. That's what the central bank does. So when there's not enough money in the system, they expand their balance sheet, okay? And banks, individual banks can also expand their balance sheet. It's like expanding their business. So they have more deposits and more loans, and they just expand it out. Of course, if you just expand it out, your reserves and all other things have to increase too, because if there's a small change in things, the numbers are huge all of a sudden, right? So these velocities, they become really big because that arm is getting big at the same rate of interest, woo, huh? Okay. And the other thing is called shrinking the balance sheet. Okay. So you can see this kind of problem also, like you have this couple, but now you, instead of one canonical variable, which is just this rotation, you also look at the distance between these two. This is like a real two-body problem, right? You can do it in space and they kind of tumble around like that. And you calculate from the center of mass the angle and how far they're probably going apart or whatever. Huh? So what's cool about this is that you're basically there. You can now set up a Lagrangian. This r was held a constant, so this r dot wasn't zero, but now you can put it in. There's the rate at which you're expanding your balance sheet. You can just throw this in there, right?
So that's your control.
Yeah, the central bank uses it as a control input, right? That's quantitative easing. That's so regular interest rate easing is changing this guy.
So now you don't have the rigid body anymore, but you're just keeping the masses at place.
So if you look at the omega, which is the theta dot, that is manipulating the interest rate. Huh? So they do that too. That's the first thing they do. They're lower interest rates or they're up it. And then this one, they call QE, quantitative easing. That's expanding the balance sheet. Either way, you can affect the dynamics of the system, right?
And that's on ECB level, and at the ALM management level, you can just independently add more liabilities or add more assets.
Yes, exactly. So that's like what they do.
Controlled current source.
Yeah, and so the ALM can do two things. Well, this is what they can do.
Yeah.
And they could also try to change the interest rates that they want to charge, but they definitely can control this one. You see, that's what's going on, huh?
Yeah.
They have to keep track. Most likely what they have here, this stuff gets eaten up probably, and spent immediately. But this thing you want to keep track of, so you're definitely going to have some kind of convenience on how big your balance sheet is. Is this getting too big, Because you can see small changes are going to give huge, changes, and you're going to have reserve accounts and other accounts that are going to have to stabilize this thing, so you can meet the velocities that are requirement. Those are the payments, okay? But that's exactly right. You can always control these velocities or the prices that belong to them. So you can also change the price. It's some other kind of, that's balance sheet risk. This is what the central bank or the Federal Reserve has, Just when you expand your balance sheet, you're highly leveraged usually, unless you have a lot of capital. So, So this is what they call leverage, right? If this thing is big. That's what we call leverage too, doesn't we? So there's something very pretty about this picture for the engineer, because all these terms get brandied about, expanding the balance sheet, blah, 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 You have no idea what they're talking about. They probably don't either. It doesn't matter. They've said it enough so that they think they know what they're talking about, and most engineers are like that too. So we all recognize that, But in any case, what this lecture will show you is things that you've said all along now can be fitted in stuff that they say all along. And I believe you're in much better shape. Look, I stopped the lecture here. I thought this is more for students, especially Brit and stuff. That you can calculate the surplus. You can look at these prices. What are they? How can you control that whole system? Et cetera, et cetera, et cetera. I think our approach is way more powerful. It just puts everything in a framework. You don't have to guess. You don't have to do regressions. You don't have to do any of that. All right. Cool. So with that, this lecture is ended, and we'll see you all soon, I hope.